Ladies and gentlemen, let's continue with Chapter 8 on internal forced convection. We are making use of the textbook of Cengel and Ghajar. We've done all the theory in the textbook, consisting out of the average velocity and temperatures in an internal duct, the entrance length, the general thermal analysis. I've mentioned to you that paragraph 8.4 is very important. You need to work through it in detail, and you need to be able to distinguish between problems of constant heat flux and problems where you've got a constant wall temperature. Then we've also did laminar flow in tubes. The laminar flow, we have seen that if the flow is fully developed and you've got a constant heat flux, the Nusselt number is 4.36. If it is a constant wall temperature, it will be equal to 3.67. Then the last part of the textbook was turbulent flow in tubes, and there were about 5 or 6 equations that I've showed to you that you can use, from the oldest ones to the most modern ones of Glinsky. We are going to conclude this chapter by doing a few examples. I've done it with a previous lecture where we've looked at a problem of constant heat flux. Now we're going to look at another problem, another example, but in this case where we've got a constant wall temperature. So in this problem is an air conditioning duct. The inner temperature of the chilled air is 10 degrees Celsius, and the volume flow rate of the air is equal to 0.15 cubic meters per second. The duct is 40 meters in length, and this outside temperature is 40 degrees. And the question, or what is being asked, is to determine the heat transfer rate from the duct, or from the outside to the inside, and what will the outlet temperature be. Normally these air conditioning ducts is in ceilings, so if that is maybe the upper floor there, then we've got a ceiling here, and all around typically what is given to us is that the temperatures are 40 degrees Celsius all around this duct. So for this reason, we're going to say it is a problem where we've got a constant wall temperature. So it's a problem where Ts is equal to constant. Ts is equal to C is equal to a constant. When we do these types of problems, as you've known by now, we have to calculate the Reynolds numbers, the Nusselt numbers, etc. And with all of it, we need the properties. So we have to get the properties of the air, but in this case, the inner temperature is given as 10. The outlet temperature is not given. Okay. So what do? You guess. You guess, work through the problem, and then depending on the result, you will adjust it. So if you now look at this problem, what would you guess would the outlet temperature be? All of you. Anybody? How much? 35. Okay, there's a 35. 20. 25. Okay. So what I'm going to do is I'm also going to guess 20. Okay. So therefore, the bulk temperature is going to be the inner temperature and the outlet temperature divided by 2, which is of course 10 plus 20 divided by 2 is going to be 15 degrees Celsius. Okay, and now at a temperature of 15 degrees Celsius, and from the tables in the textbook, you can go and get the properties of the air. The properties, density is equal to 1.209 kilograms per cubic meters. The Cp value is equal to 1004 joules per kilogram Kelvin. The thermal conductivity K is equal to 0.02476 watts per meter Kelvin. The Prandtl number is equal to 0.7305, and the viscosity is equal to 1.802 multiplied by 10 to the minus 5 square meters per second. So those are all the properties at a temperature of 15 degrees Celsius. If you can go and look in your textbook, you might see that your values differ from mine a little bit. What's the reason for that? Well, the reason for that is in every one of your textbooks, there's a CD-ROM. And the name of that CD-ROM is software that you can upload or that you can download. And the name of the program is EASE, E-E-S. And it is very convenient with EASE to get the properties. So you're just going to select air, for example. You're going to put in the K value at a certain temperature, and it's going to give you all the values. So for somebody like me that's very lazy to do interpolation, I prefer to work with that program. And for many of you with your designs and your research projects, I would recommend that you take a look at this program. The one in the textbook is a version that I don't think you can save things with, and I think you cannot print. But there is one available in the department. We've got a license for it, and you can use it for a period of 1 year for free. Professor Sharafpour is a person that you can ask this program for. Right. Let's also look at the volume flow rate. The volume flow rate is equal to the velocity multiplied by the cross-sectional area. So we see that we're going to need the cross-sectional area. So let's calculate the cross-sectional area. The cross-sectional area is 0.6 multiplied by 0.2, which is equal to 0.12 square meters. The cross-sectional area through which the flow of the air goes through, so it is 0.6 multiplied by 0.2, 600 millimeters by 200 millimeters. The other area is going to be the area through which the heat transfer is going to occur. The area through which the heat transfer is going to occur would be this outside area, all around the perimeter. So that would be equal to the perimeter multiplied by L. The perimeter is equal to 2 times 0.2 plus 0.6. Therefore, 200 millimeters plus 600 millimeters is 800, multiplied by 2 is 1.6 meters in terms of the perimeter. Okay, multiplied by the length, which is 40, and from that we can get the surface area as 64 square meters. Okay. In terms of just going back to the volume flow rate and the velocity, the volume flow rate has been given as 0.15. It's equal then to the velocity multiplied by the cross-sectional area is 0.12. So we can calculate the average velocity as equal to 1.25 meters per second. Right, now that we've done a little bit of preliminary work, we've got all the properties, we've got the velocities, etc. Where are we going to? We need to get, if we work with the heat transfer rate or that outlet temperature, we need the heat transfer coefficient. To get the heat transfer coefficient, we need to get the Nusselt number. And usually to get the Nusselt number, we also need the Reynolds number to know if the flow is laminar, turbulent, or whatever. So if you just think ahead, you need to realize that in terms of the Reynolds number, which is equal to rho Vd divided by the viscosity, we've got everything except the d, or the characteristic length. Okay, so in this case it is not a circular tube. Therefore we need to make use of the definition of the hydraulic diameter to get a characteristic length, and we're going to use that to get the Nusselt number for. So we need to realize that we need to transform this cross-sectional area to that one, and we do that to get the Reynolds number based on the hydraulic diameter. We need to get the Nusselt number based on the hydraulic diameter so that we can get the heat transfer coefficient. That is the only reason why we're going to make this transformation, changing it to a circular tube. Because later on, we will have to work with a certain area. And the area here of this is not going to be the same as that. So do not mix the two. You need to realize that we do this so that we can get this. Why? Because there are not general equations available for a duct like that. That's the reason for it. But we know from experiments, if you go and calculate the hydraulic diameter, you can calculate the hydraulic diameter and then the Reynolds number from it and then the Nusselt numbers, and then you can get approximate the right answer. So the hydraulic diameter is equal to 4 times the cross-sectional area divided by the perimeter. The cross-sectional area through which the flow flows is equal to this total area, and that is equal to 0.12 square meters divided by the perimeter, which is 200 plus 600 is 800 millimeters multiplied by 2 is 1.6 meters. Okay? If we do it again, it's just the perimeter, which is 200 plus 600 is 800 plus another 200, 1 meters, plus another 600 millimeters, 1.6 meters, the wetted perimeter. So the hydraulic diameter then works out as 0.3 meters, 300 millimeters. Then we calculate the Reynolds number based on the hydraulic diameter, which is rho Vd divided by the viscosity. The previous lectures, I've brought to your attention that there is a derivation where you can say the Reynolds number is equal to 4 times the mass flow rate divided by the viscosity, and I think d or something like that. Remember, this is just valid for a circular tube. We do not work with a circular tube now. Yes, we are doing this in terms of getting this, but the reason for that is just to get the Reynolds number and the Nusselt number. So if we go and calculate it, it is equal to the density, which is equal to 1.209, multiplied by the velocity is equal to 1.25. The hydraulic diameter is 0.3, divided by the viscosity, which is equal to 1.802, multiplied by 10 to the minus 5. And that will give us a Reynolds number of 25,167. 25,167. That is about 10 times larger where transition will occur. So we can assume that the flow would be turbulent. If we didn't do that, we would have the problem in terms of getting the Nusselt number to decide between a Nusselt number of 3.67, which we have for a case where we've got a constant wall temperature, or the Glinsky equation, or the Cedar and Tate. So you need to calculate the Reynolds number so that you can determine if the flow is laminar or turbulent, and so that you can then therefore use the right equations. What we also know is because the Reynolds number is so high, and we typically now look at this tube of 40 meters, and we think of the heat transfer coefficient, then the flow would be fully developed within 10 diameters. 10 diameters is about 3 meters. So it is less than 10% of the total length of the tube. So the heat transfer coefficient in the first 3 meters would be higher, but after that it's going to be constant. So for more than 90% of the length of the tube, the flow is fully developed. And therefore, it's a good assumption to say we disregard this part of the equation. Right, in terms of equations which are available that we can calculate the Nusselt number with, for turbulent flow, there are 5 or 6 or 7 of them available. I normally choose the easiest one, which is equal to 0.023, multiplied by Reynolds to the 0.8, multiplied by Prandtl to the n. Okay. I use the easiest one because I'm lazy. So that is equal to 0.023. The Reynolds number we've determined as 25,167 to the 0.8. Prandtl, we've got it there from the properties, is equal to 0.7305. And for that, we use a value of n equal to 0.4. Okay. Why? Because you've got an option of n for heating or cooling. If the fluid is being cooled, n is equal to 0.3. If it is being heated, it is 0.4. So we need to use 0.4. And if we use that to calculate the Nusselt number with, then the Nusselt number is 67.27. Okay, and we can maybe say it's the Nusselt number based on the hydraulic diameter. Now the Nusselt number based on the hydraulic diameter is equal to the heat transfer coefficient multiplied by the hydraulic diameter divided by K. The Nusselt number we have now determined as 67.27 is equal to the heat transfer coefficient, that is what we want to determine, multiplied by the diameter is equal to 0.3 divided by K, the thermal conductivity, which is equal to 0.02476. And from that we can get the heat transfer coefficient as equal to 5.55 watts per square meter degrees Celsius. Right, now it's so easy to calculate the heat transfer rate. So the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the surface temperature minus the bulk temperature. The heat transfer coefficient is equal to 5.55. The surface area is equal to 64. The wall temperature is 40. The bulk temperature is 15. And therefore the heat transfer rate is 8.885 kilowatts. Okay? Now that we've got the heat transfer rate, we can calculate the outlet temperature. We can say that the heat transfer rate is also equal to the mass flow rate multiplied by the Cp multiplied by the outlet temperature minus the inlet temperature. The heat transfer rate is equal to 8.885 multiplied by 10 to the 3. The mass flow rate is equal to the density, which is equal to 1.209 multiplied by the volume flow rate, which is equal to 0.15 multiplied by the outlet temperature minus the inlet temperature, which is, 10. From which we can calculate the outlet temperature as 58.79 degrees Celsius. I see at least there are some of you laughing. Yep.
The mass flow needs to be times by the area of
the mass flow rate would be equal to the density multiplied by the volume flow rate. The density is equal to 1.209 and the volume flow rate 0.15. Sorry?
I thought it was velocity.
Okay. What's wrong? Q is supposed to be negative. In heat transfer, we don't work with negative. We sort of always know. Yes? Sorry? CP, oh, I forgot to put in the CP value. You can put it in there, it's 1004, you're right. Okay? Yep.
Shouldn't we use the log mean difference?
Yes.
Instead of
yes. Okay, so this is incorrect. Okay? That is just valid for a constant heat flux case. We've got a constant wall temperature, so therefore that is incorrect and that is incorrect. Fortunately, you can at least see it there with a temperature, which actually shows that the outlet temperature is higher than that of the wall. It can't be. Okay. So to correct this, and that is why I've asked you, I still always do it, I always make a sketch. That is my wall temperature. The wall temperature would be 40 at the inlet, it would be 40 at the outlet. Okay. The inlet temperature of the air is 10. And because we have a constant, and here is our temperature that we have guessed for the bulk temperature. There is bulk is 15. Okay. So our temperature distribution of our air is not that of a straight line. That you get with a constant heat flux. The temperature distribution is going to be something like that. So we cannot do the calculations with this delta T. We need to get the right delta T. And for that we need to get the LMTD, the log mean temperature difference. So let's do that. I like to always work with the NTUs. It's not specifically like that in the textbook. But the NTUs, you can go and calculate it as the heat transfer coefficient multiplied by the surface area divided by the mass flow rate and the CP. Okay. The heat transfer rate we've calculated as 5.55. The surface area is 64. Divided by the mass flow rate is equal to 0.1814. I should have actually written it here also. So it is equal to, the density is equal to 1.209, 0.15, and the mass flow rate is equal to 0.1814 kilograms per second. In case you can't read my writing there, the density multiplied by the volume flow rate, the density is equal to 1.209. The volume flow rate is 0.15, and that gives us 0.1818 kilograms per second. Actually, sorry, 0.1814. Right, multiplied by CP, and CP is 1004, and the NTUs is equal then to 1.952. Okay, the NTUs. Now this is actually a relatively high value. I've showed you previously that if the NTUs is equal to 3, then it means that that temperature and that temperature are going to be approximately the same. So with this NTU value, you can really expect quite a significant increase in temperature. Now that we've got the NTUs, we can calculate the outlet temperature based on the equation that we've derived previously. And that is the outlet temperature is equal to the surface temperature minus the surface temperature minus the inlet temperature E to the minus NTUs. In the textbook they use the heat transfer coefficient multiplied by the surface area divided by the mass flow rate Cp. As I've mentioned to you, if you just put it in there, you do the calculation, you do not really have a very good physical understanding or expectation of what is going to happen. So if we complete the calculation, okay, it is equal to 40, the surface temperature, the inlet temperature is 10, E to the minus 1.952, and that gives us a temperature, an outlet temperature of 35.19 degrees Celsius. So one of you have guessed 35 for the outlet temperature, you were very close. Okay, 35.19. Now any air conditioning engineer will get a heart attack for an installation like that, and I think you also. So if you can just think of the ducts going into this venue, I don't think the air conditioning is working today, but at the chiller, the air is being produced at 10. If you've got a 40 meter duct and the air is coming in here at 35.19, that is not what we want. Okay, we still need to calculate. We've calculated the outlet temperature now, but we still need to calculate the heat transfer rate. So getting the heat transfer rate, we need the LMTD, and the LMTD is very easy to calculate. Okay, so before you write, just look at me. 40 minus 10 is a delta T difference of 30. Okay, minus this temperature difference here, which is equal to 4.71. Okay, divided by the lim of those two terms, 30 divided by 4.71. Okay, so it's this temperature difference minus that temperature difference, and the lim of these two terms, you just divide by them. Okay, and that is equal to 31.8 degrees Celsius. Okay? Ladies and gentlemen, today you shouldn't believe anything I do. Okay? Because this is also incorrect. You say no. Okay. That's the advantage of having a sketch. Just look at this. 40 minus 10 is 30. We say that this average temperature difference is 31. It can't be. It is also sort of not possible for it to be 0 or less than 0. Okay. Because what we actually want, and you can just always look at it. If you look at that and you're going to say, what is really the average temperature difference? We need to integrate this. Obviously, you don't know exactly how this line looks like, but if you just look at that, you will say, no, I expect the delta T to be something there. It can't be more than 30. So it's very easy to make a calculation error. So that temperature should be equal to 13.19. So 13.19, if we look at that, we will say that delta T is 13.19. 13.19 degrees Celsius. Now we can calculate the heat transfer rate. The heat transfer rate is the heat transfer coefficient multiplied by the surface area multiplied by LMTD. Okay. Again, remember, do not get confused, because now students look at this and they use the surface area of this duct of 300 millimeters. It shouldn't be this surface area, it should be this surface area. Okay. Why? Because we only use this approach to get the Nusselt number, to estimate the heat transfer coefficient. That's why we do it. But for the rest, you always work with the values. Here also, the surface area was not that of a circular tube, it was of the duct itself. So it is equal to the transfer coefficient, which is equal to 5.55, surface area 64, multiplied by the LMTD, which is 13.19, and that is equal to 4687 watts. That's not the type of answer that I like. The engineering answer is 4.7 kilowatts. Okay. It is always, if there's a possibility that you can check your result using another approach, then I would always recommend that you do that, and that is what you can do in this case. You can also say that the heat transfer rate should be equal to the mass flow rate, Cp multiplied by the outlet temperature minus the inlet temperature. So we always write the delta T's so that the heat transfer rates are positive and not negative. The mass flow rate is equal to 0.1814. The Cp is equal to 1004. Outlet temperature is equal to 35.19. Minus the inlet temperature is 10. And fortunately, we get exactly the same answer, 4.7 kilowatts. So that is just to check if your calculations are correct. Right, my question to you, ladies and gentlemen, are you now satisfied with this problem? If you look at it as an engineer critically, what would you say needs some attention? Exactly. So when we started with getting the properties, I've estimated that the outlet temperature is 20, and it's much higher. So we need to go and get a new bulk temperature. We need to get new properties and redo the problem. Now in the test and exam, I'm not going to expect of you to do that. However, you're definitely going to lose 1 mark if you didn't mention it here to me that you should iterate. Okay? So if you if we would now, okay. So you need to iterate and calculate the new bulk temperature, which is now the inlet temperature plus the outlet temperature divided by 2. The inlet temperature is 10. Our outlet temperature is 35.19 divided by 2, and that is equal to 22.87 degrees Celsius. So the bulk temperature is now higher than before. So at this temperature, you can go and get the properties. Properties at 22.87 degrees Celsius. So go and get all the properties at 22.87. Go and recalculate the Reynolds number, which would then be equal to 24,003. Previously it was 25,167. So we see it's still turbulent. Go and calculate the NTUs, equal to 1.973. Go and calculate the outlet temperature. Then you're going to get 35.83 degrees Celsius. The heat transfer rate is going to be 4581 watts or 4.6 kilowatts. Okay, question?
I want to ask about, should we iterate to a point where the guess is equal to the output of the calculation?
Yes, you should iterate to the point where your guess is obviously, where your results do not change anymore, the outlet temperature and the heat transfer rates. Okay. Now I'd like to do a little bit of an exercise with all of you in terms of, I suppose everybody of you at least stay here somewhere during the week, and I don't think there are anybody staying in Cape Town and you're coming in from Cape Town every day to class. But how far do you stay from the university?
20 kilometers.
10? 20 kilometers, right? 20? You? 7? 7?
20 as well.
20? Anybody else? 3? Okay. So, if we did a calculation, and from the calculation I say you stay 20 kilometers from the university, you would say it's spot on. Okay. So you'll see that most of you actually almost use one significant figure to say how far you stay from the university. So that's why in engineering, you know, you're not going to give an answer of 4,581. 4.6 kilowatts, 4.6 kilometers from university is very accurate. It's not bad. Especially if we take into consideration that the calculation of the heat transfer coefficient is plus or minus 20%. So it's quite accurate. So if you just look at this in terms of the first calculation, which was totally out, to the second one, it almost changed nothing. But now you can say to me, oh, but maybe you've jipped out a little bit. It's maybe because of the fact that you've selected an outlet temperature of 20. What if I have selected that my bulk temperature is 10? Okay. I've selected a bulk temperature of 10. So therefore, I've made the assumption that there's going to be no temperature increase. If you've done that, and if you've done all the calculations, then the outlet temperature would have been 35.68. 35.68 against 35.19. Heat transfer rate would be equal to 4.8 kilowatts. Okay. 4.7 to 4.8 kilowatts is nothing between friends. Even worse, if we've said I would choose a bulk temperature of 40, okay, and if I would redo the calculations, I would get an outlet temperature of 36.02 and the heat transfer rate of 4.3 kilowatts. So you will see that the problems are not that sensitive to changes in properties, but you always need to think about it. It is important. Let's suppose, in terms of your critical evaluation of this problem, you've said, but you know, this fact that you've used the Dittes and Boulter equation, it's maybe not such a good approach. Maybe you should use a little bit something more accurate, like the equation of Glinsky. Okay. So let's do that. Equation of Glinsky. If you would do that, and you would go and calculate the Nusselt number according to Glinsky, it would be 62.84. The heat transfer coefficient would be equal to 5.187. Outlet temperature would be equal to 35.15, and the heat transfer rate would be equal to 4.6 kilowatts. To be able to get this Nusselt number, you first need to get the friction factor. How do you get the friction factor? Well, there are two approaches. The one is, you can go and look at your Moody chart. The friction factor is a function of Reynolds number. And as I've discussed previously, this is the case for the smooth tube. Epsilon divided by d is equal to 0. And then you get all the others there. Normally, these ducts are made from galvanized steel. If you go and measure that surface roughness and you divide it by the hydraulic diameter, the epsilon divided by d is normally in the order of 0.40 and then something. So for all practical purposes, it's a smooth tube. So at this Reynolds number, you can go and get the friction factor, or if you want to calculate it, you can calculate it from this formula. The friction factor is equal to 0.790 multiplied by the ln of the Reynolds number minus 1.74 to the minus 2, and from there you can calculate it as 0.02468. When I do these calculations, I always just go and check myself in the Moody chart to see if it is approximately correct. Okay, so you need this friction factor in the Glinsky equation, excuse me, to calculate the Nusselt number. Now let's make this problem a little bit more interesting by doing it and saying that let's put some insulation around this duct. Some insulation. And the thermal conductivity of the insulation is equal to 0.04. Not the H value, the K value, excuse me, the thermal conductivity. Thermal conductivity is equal to 0.04 watts per meter Kelvin, 50 millimeters of insulation all around. Okay, now I hope that you can still remember from your chapters 1 to 3 in the textbook of Cengel and Ghajar that what was done there is to say that the heat transfer rate is equal to the temperature differences divided by total resistance. Okay. And the total resistance would be equal to 1 divided by the heat transfer coefficient on the inside multiplied by the area plus L divided by Ka plus 1 divided by the heat transfer coefficient outside area on the outside. Okay. Now just be careful, this L is not the length of the duct, it is actually the thickness of the insulation. So I'm going to call that X, thickness of the insulation X. So therefore, it means that this problem, if we've got this duct, is being driven by 3 terms. The one is the heat transfer coefficient on the inside, that term on the inside, and then there's one on the outside. So we've got a resistance term here, which is the resistance on the inside. Okay. Then we've got the resistance through the galvanized plate, and then we've got the resistance on the outside. Now the resistance on the outside is now insulation material. Okay. But then there's another resistance, and that is the resistance on the outside, which is this 40 degrees Celsius here in the sealing area around the tube. Okay. Now to get this heat transfer coefficient, we are going to do that in the next chapter because that is natural convection. So we are going to not take that one into consideration and assume that that is the temperature of the insulation material all around. That is the galvanized steel, and that is the resistance of the air. So if we typically look at this problem without insulation, material, then the total resistance is just going to be 1 divided by the heat transfer coefficient on the inside multiplied by the area. And that is 1 divided by 5.55, it's 64, and that gives us a value of 0.002814. Watt per square meter, watt per degree Celsius. If we look at the resistance with insulation, then the total resistance is going to be equal to 1 divided by the heat transfer coefficient on the inside multiplied by the area on the inside plus X divided by K, the area. So remember, this third term we are not going to take into consideration now because it's only with the next chapter when we can calculate it. Okay, so that term is the same as previously, but now we've get the thickness of the insulation, which is 50 millimeters, divided by the K of the insulation is equal to 0.04, multiplied by the surface area is 64. Now I can write down the answer, but I specifically want to do it like this, writing it in 2 terms. 0.002814 plus 0.01953. So I want to write down the 2 values there. And that's always a very important exercise because what does it show? It shows that all the resistance is actually now in the insulation. This value is 7 times larger than that value. Okay, and the result of that is equal to 0.022345. Okay, now we're not going to have enough time to work through this problem, but if you now use this resistance in terms of going to the calculations of the NTUs, there you see the heat transfer coefficient multiplied by the area, so that can be written as the resistance. So you can take that out, you can write it as the resistance. And then you can go and do it now with the insulation. And if you do it with the insulation, then, so obviously you need to do some work in between, then the outlet temperature is going to be 16.53 degrees Celsius with 50 millimeters of insulation. If you redo the calculation with 100 millimeters, it's going to be 13.17. If you do it with 150 millimeters, it's going to be 12 degrees. So 2 degree temperature increase along the duct length. Any questions, ladies and gentlemen? If not, thank you very much.